Anyway, so let me just spend a few minutes reviewing what we covered last time. Went a little bit fast at the end. So on the marked lecture notes, I did add another example. So let me just go over that. Okay. Okay, so the bottom line is if you introduce dopants into a semiconductor sample, you can directly influence the concentration of electrons and the concentration of holes. And generally, the concentration of the majority carrier is going to be approximately equal to the net dopant concentration, okay? And the concentration of minority carriers, which are holes for n-type material, is going to be equal to Ni squared over the majority carrier concentration. Okay, so in case it wasn't clear from the example I went through last time, this bottom line is if you dope something with donors, then you essentially end up with equal concentration of electrons as to the concentration of donors. And then you can just calculate the minority carrier hole concentration, knowing that the product of minority carrier and majority carrier equals Ni squared. Okay? So then for p-type material, then it's holes, positively charged mobile carriers, are the majority carrier. And so the concentration of holes is given by the net acceptor concentration. And the concentration of electrons is going to be equal to Ni squared over p. Okay? All right, and the key is that there's a huge, many orders of magnitude difference between the majority carrier concentration and the minority carrier concentration. Okay, any questions left over from the last lecture? All right, so let's go on to today's lecture notes. So we're going to talk about, well, we introduced the energy band diagram last time, and the energy band diagram allows us to keep track of electron potential or potential energy as a function of position within your semiconductor device. But another thing we need to know is, well, how many carriers are there? How many electrons and holes are there in different regions of your semiconductor device? So that's the point of the discussion today. We're going to introduce something called the Fermi level, and it's the position of the Fermi level that helps us keep track of the concentration of electrons and holes in different parts of the semiconductor. Okay? So if we have a semiconductor, oops, oh, all right. So one question left over from last time. Sorry, I'm going to make Scott stand a little longer. I didn't really explicitly say, but why do we only keep track of electrons occupying states in only two bands, the valence band and the conduction band? Why is that the case? If we want to keep track of how current flows in a semiconductor material, why do we only need to keep track of electrons occupying states in the valence band and in the conduction band? Yes. Right, so the answer was yes. Those bands are the ones that have mobile charge carriers. Actually, there are bands below the valence band, right? The core shell, the filled electron shells, they represent lower bands of energy, but they're all filled. And so when you have if you imagine a tube filled with liquid, if it's completely filled and you tilt it, there's not going to be any net movement of that liquid, right? And then also on the other extreme, above the conduction band, there are bands of allowed energy levels, but those are pretty much empty, so they're not going to contribute to current conduction. So even if you have an empty jar or a tube or a full tube, neither of those is going to allow net current flow or net fluid flow. Okay, so that's why we only keep track of the conduction band, what's going on in the conduction band and the valence band. And so what do you think we're simulating here with this analogy on the right? What's being done to the semiconductor if it's analogous to tilting these tubes to the right? Pardon me? Electric field, exactly. So let's say if the electric field, it's kind of equivalent to an electric field going this way. So electrons that are negatively charged will want to go to the right, and holes which are positively charged would like to go to the left. Right? So in other words, the fluid, you're getting net movement of electrons in the valence band states to the right, but that's the same as having the positive charge associated with the missing covalent bond moving to the left. Okay. All right, so the question is then, how do we know how many electrons have enough thermal energy to move from the valence band of allowed energy states to the conduction band? So, okay, so that's what we're going to cover today. So the Fermi-Dirac distribution gives us the answer. Okay, so this is all derived assuming thermal equilibrium. So the definition of thermal equilibrium is that only the carriers, electrons and holes, exist due to heat. Okay, and you're not shining light on your semiconductor to generate electron-hole pairs. You're not applying electric field to try to pull electrons out of the covalent bonds and so on. Okay, so no external forces, just heat. And under thermal equilibrium, you always have one, because the atoms are vibrating, because you heat up a solid, the atom's going to have some average energy, so they'll vibrate. And so every once in a while you'll generate an electron-hole pair. Right? An electron will escape a covalent bond, and you'll end up with a mobile electron and a mobile half-filled covalent bond. And every once in a while, an electron and hole will meet and annihilate each other. So basically, overall, nothing is going to change, even though things are happening. Right? Electron-hole pair generation is occurring, recombination is occurring, but every process is exactly canceled out by some other opposing process. Okay. So basically, when a semiconductor is heated up, let's say at room temperature, above 0 Kelvin, basically the atoms are all vibrating in their lattice, about their lattice positions, and that gives energy to the electrons so that some of them actually escape the covalent bonds. Okay, so the simple demo here is going to basically show you this. This is in Professor Hu's textbook. But basically, this vibrating table is analogous to thermal excitation. Okay, so if you have a vibrating table, at any point in time, you sort of have an average number of particles that have enough, that are at a certain height, right? They have a certain amount of total energy. And the number of particles decreases actually exponentially as you go higher up, right? The probability of finding a particle at some height goes down exponentially as you go higher up in height. Okay, so that's the simple demo that we want to show here, if we want to try. Okay, but yeah, you think it'll work? You want me to hook this up? Okay, so this is for the benefit of people who are going to watch this on webcast. You think this works? Okay. I don't even know how to turn off the lights. Is that too dark? Okay. Can you see that? So Scott. The other combo? Oh, you mean like this? Okay. So Scott built this little thing where we can actually cause this table to vibrate, and there are actually BBs in this container to simulate electrons in a lattice. So he's going to basically turn up a waveform generator to modulate the magnetic field generated by a coil, positive and negative polarity, and there's a magnet attached to the bottom of this container that'll just cause this thing to move up and down. Okay. So he'll demonstrate that. Anything in the... Oh, yeah. Okay, sorry. Right, so so this is like near room temperature. But if you turn up the vibration, it'll be very noisy. You do it really high, like really high. Right, okay, slow down. Right, so on average, the larger the vibration, that's simulating higher thermal energy, right? So it's higher temperature. So the question is, let me see if you remember from last time. How would you simulate adding dopants to this system? Add lighter balls. That means you add electrons that are easier, that can escape covalent bonds more easily. Then that means you're changing the band gap of the material. So that's true. You could, but adding the dopants usually doesn't change the band gap of the material. That's a fundamental property of the semiconductor. That's right, change the depth of the container. So let's assume that to reach the conduction band edge, you have to get to a certain height, right? So basically, that's what this is. If I add dopants, let's see, right? So let's say there are a few dopant atoms, like 20, right? And the electrons start out at a higher level. Now you shake it. The probability of finding an electron at a certain height becomes pretty much 100%, right? Right? Okay. All right, that's good. Right, so basically that's the idea of adding dopants. You actually introduce electrons that are close to the conduction band edge. So just a little bit of thermal excitation will generate a lot of mobile electrons in the conduction band to contribute to current flow. Okay, I think that's it. Thank you. Yeah. Sorry, the camera is not the best, but that's great. Very noisy. Yeah. So that with that analogy, let's say you go to very high temperatures, like it was really noisy. At very high temperatures, you already have a lot. You naturally get a lot of electrons way up at higher energy, right? In other words, at very high temperatures, you can actually get a lot of. Let's see. From last time, that was the point of this plot. See, if you go to very high temperatures, then naturally you'll have a lot of electrons that have enough energy to reach the conduction band. They'll naturally be up there. And that can actually dominate. So the number of electrons donated by the dopants actually might become negligible compared to the intrinsic, thermally generated electrons. Okay? So that's the point of this plot. Thanks, Scott. Okay. Any questions in general about this thermal equilibrium concept? All right. So the Fermi function basically is an analytical expression that tells you what is the likelihood that an electron is at a certain energy level. Okay? And so it's given on this slide here, F sub E. And just qualitatively, if you look at it, there's a Fermi level, or Fermi energy, let's call this. E sub F is defined to be the Fermi energy. Okay. And can somebody evaluate this expression at the Fermi energy? If E equals the Fermi energy, what is this Fermi function's value? 1/2. Right, so the Fermi level, conveniently, you can remember it as the energy at which the probability that an allowed energy state is occupied is 1/2. Okay, so that's good to know. So that the Fermi function at EF equals 1/2. Okay, what about, I think I have it here. Oh yeah, okay. So in a system at equilibrium, sorry, I should erase that. In a system at equilibrium, there's only one Fermi level. Okay. In other words, so a Fermi level at equilibrium, there's no net movement of electrons back and forth. So that means any point in your semiconductor is just as attractive for an electron to be as another. And so the Fermi level actually in chemistry you refer to as the electron chemical potential. So if the Fermi level, if we say that there's only one Fermi level in a system at equilibrium, what that means is that if you plot EF as a function of position, it's just a flat line. Okay, that's what it means when we say that there's only one Fermi level in a system. Okay. All right, so we covered the case where if E equals EF, what if E is the energy that you're interested in is much greater than the Fermi level, is much higher than the Fermi level? What approximately is the value of the Fermi function? 0, right? So f of E, so approximately 0. It's vanishingly small. If the energy level is well below the Fermi function, then what is this approach? 1. Very good. We already did this. Great. OK, so this is the actual plot of the Fermi function. The Fermi function does depend on temperature. OK, so that's in this exponential term, this energy. The energy difference between, well, the difference between the energy of interest and the Fermi level normalized to kT. So that's 26 milli-electron volts. So the Fermi, the probability of occupancy of a state at high temperatures, okay, so this is a plot of the Fermi function, okay, as a function of the Fermi level. And as we just showed in the previous slide, if the energy level is much below the Fermi level on the left, then it approaches 1. And if the Fermi level is much higher than, sorry, if the energy level is much higher than the Fermi level, then it approaches 0. Right? So you know it has to start at 1 for very low energies and goes down to 0 at very high energies. And at the Fermi level, it always crosses through 1/2. Okay? Now the difference here between these curves is the temperature. Okay? So if you heat up a crystal to higher temperature, hopefully qualitatively it makes sense, the chances of seeing an electron occupy a higher energy state goes up. Right? So the probability, which is what this Fermi function is, the probability of finding an electron at a higher energy level goes up as you increase temperature. Does that make sense? Right? So at lower temperature, the probability, let's say, of finding an electron, having an electron occupy an energy level like here is low. But as you heat up the sample, more and more likely you'll see, electrons at higher energy level, at that higher energy level. Now, well, those electrons come from somewhere, right? So as the temperature heats up, the probability of finding an electron above the Fermi energy goes up. But that also means that the probability of finding an electron at a lower energy goes down, right? Because those electrons are coming from somewhere, from the valence band to go up to the conduction band. So notice then that you have probability of occupancy of an allowed energy state level going down with increasing temperature if you're talking about energy levels below the Fermi level. Okay? Right, so let's go over this simple approximation. That Fermi function is not so easy to integrate if you want to. Actually, so for a semiconductor, we really usually care about the total number of electrons available to conduct current, or the total number of holes available to conduct current. That determines the conductivity of the material. So we actually would like to integrate the total number of electrons at every single allowed energy state to find the total number of electrons. And to take that integral is sometimes it's not so convenient analytically, so we'd like to use this Boltzmann approximation. So the Boltzmann approximation just states that if the energy of interest is always much greater than the Fermi level, much greater means by more than a factor of 3k, then the Fermi function can just be approximated by a simple decaying exponential function. Okay, so in other words, looking at this region of the curve, it just looks like an exponentially decaying function, right? As long as you increase E relative to EF, this function just decays exponentially. Okay, so that's true if we're talking about like this, let's see, about here, right? In this regime here, right, where we're sort of far away from the Fermi level, so this starts to look more like a simple exponentially decaying function. Okay? Now, what about below the Fermi level? below the Fermi level, we actually, to keep track of holes, we want to keep track of states that are not occupied. So the probability that a state is not occupied is just 1 minus the probability that it is occupied. So then we can also find that it can be approximated by an exponentially decaying function of the energy below the Fermi level. Okay, so we go back here. If we only care about the difference, 1 minus the Fermi level, so this distance here is decaying exponentially as you go to energies lower and lower below the Fermi level. Okay, so 1 minus F of E is approximately equal to some exponentially decaying function of energy. Okay, so the greater the energy is below EF, the more it looks like it just decays exponentially. Okay? All right, so that's only true, keep in mind, if we're talking about energies that are more than 3 kT away from the Fermi level. So can somebody remind me, at room temperature, what is 3 kT? Well, kT is 26 millielectron volts. So it's approximately, right, so 78. OK, so let's keep that in mind. 78 millielectron volts. How does that compare with the energy band gap of silicon? Do you remember? 1.12 eV. That's the band gap of silicon. Okay, so the band gap energy of silicon is 1.12 eV. And this is 0.078 eV. 3 kT is 0.078 eV. So it's much smaller, less than 1/10 of the band gap energy. So let's qualitatively keep that in mind for later on. OK, so as I mentioned, let's derive an expression for the total number of electrons in the conduction band. So that's the total number of electrons that occupy any energy level, allowed energy level in the conduction band. So we do this by taking the density of states. Okay, so that's here. We covered this last time. So this is G sub C, as indicated here. So this is a plot. G sub C, the density of allowed energy levels is increasing, okay, because this is plotted sideways, as you go up in energy within the conduction band. Okay, so that's the number of allowed states that can be occupied. But then you have to multiply that by the probability that those states are occupied. And the probability decays exponentially as you go up in energy. Okay, so basically, you multiply those two together. Then you can get the number of electrons that are occupying any energy level in the conduction band as a function of energy. Okay, so this basically shows graphically how electrons are distributed in the conduction band. So the key thing to note here is that the tail is exponentially decaying. With increasing energy. Okay, so as you go higher and higher in energy, the likelihood of finding an electron at an allowed energy state in the conduction band goes down exponentially. And another key thing to note is that this peak is located at 1/2 kT. And actually, that's part of the next homework assignment. But anyway, the answer is 1/2 kT. So this peak concentration of electrons is located very close to the edge of the conduction band. So in other words, most of the electrons have very low kinetic energy. Okay? And as you heat up the temperature, of course, as the temperature increases, the average kinetic energy of the electrons does increase, right? So the peak moves up with kT. Okay? So this is a plot. So increasing concentration of electrons as a function of energy. And this is, again, increasing energy. Okay, so this is sometimes people will understand the plot better if you draw some electrons. But basically, this just says that there are some empty states in the valence band, and electrons have, the reason for that is because electrons have moved up to the conduction band. Okay? Qualitatively, does that make sense? This E sub C, E sub C. Okay. Then you do the same thing for holes, except now you take the number of allowed energy levels in the valence band. Again, it increases as you go down in energy. Okay? So plotting to the right is just increasing concentration. Now, instead of multiplying by the probability of occupancy, you multiply by the probability that those states are empty. So you have to multiply by 1 minus F sub E. And as I mentioned, in this tail region, it's just an exponentially decaying function. It's decaying towards 0. I should have mentioned. So this is like 1, and this is 0 here, right? So now you take this, multiply by that, and you can get the distribution of holes. In other words, the distribution of empty allowed energy states in the conduction band. And again, this peak is located 1/2 kT away from the edge of the valence band. Make sense? Okay, so if we only care about the total number of electrons, we're not interested in the energy distribution, we have to integrate this. So we take the integral across the conduction band range of energies to find N. And same thing to find P, we have to integrate this product as a function of energy within going down to the bottom of the valence band. Okay? All right, so let's do that. That's what's done on the next 2 slides. N is the integral of the conduction band energy density of states times the probability of occupancy. And what we can do to make this integral easier is to use the Boltzmann approximation. So we just substitute a simple exponentially decaying function for f of E. And conveniently, we can integrate to, let's say, infinity. It doesn't matter if we integrate to the top of the conduction band or to infinity, because basically we're assuming that all of those energy levels up there are not filled anyway, because we assume that f of E is vanishingly small above the top of the conduction band. It just makes the analytical expression easier. So it turns out then we get a nice simple expression for the electron concentration. It's an exponential function of this energy difference. So basically it's the difference between the conduction band edge and the Fermi level. That will basically determine what the concentration of electrons is in your sample. So in other words, if you want to keep track, if you want to indicate that there are a lot of electrons in your sample at a certain location, then the Fermi level, you should draw the Fermi level close to the conduction band edge. Okay? So last time I talked about the effective mass. So the effective mass that we use here is the same one as we use to calculate the density of states. Okay, so let me see if there's something. Any questions about this integral? Okay, so let me talk about this term here. This is called the effective density of states at the conduction band edge. And actually, this number is, for your reference, it's 2.82 times 10 to the 19 per centimeter cubed. Okay, so can somebody offer an explanation why that N sub C would be called the effective density of states at the conduction band edge? Well, here's a hint. What does this term look like here? E to the minus E sub C minus E sub F normalized to KT. What does that remind you of? Fermi function. It's basically, yeah, the approximation of the Fermi, the probability of occupancy of an allowed energy state. Where is that energy state for this probability, corresponding to this value of probability? At the conduction band, right? So the conduction band edge, right? So it's E sub c. So this is the conduction band edge energy. So E sub c minus E sub f. This term here looks like it's just the probability of occupancy of a state whose energy is located at E sub c. So basically, if all of the electrons were located somehow at the edge of the conduction band, then this formula would, at this particular value, n sub c, then this formula would give us the correct number of electrons in this sample. So just effectively, it just looks, if all you care about is the total number of electrons, then you don't really care how, and then you don't care how they're distributed in the conduction band. For all you know, for all you care, basically they're all located at this energy level, at the conduction band edge, and they have a certain density of states, n sub c, capital N sub c. Okay, sorry, there was a question first here. Okay, so the question was, what happens when EC comes close to, EF comes close to EC? Yes, the Boltzmann approximation breaks down, right? So that's a good question. So this integral is over all of the energy levels in the conduction band. So basically, we're performing this integration over the conduction band. So this is assuming then that this conduction band, let's just draw, let's say, a Fermi level here. This is assuming that the conduction band edge is at least 3 kT away from EF. Right? Otherwise, you can't use that Boltzmann approximation. Right? So basically, we're assuming that EF is nowhere very close to E sub c. Otherwise, that expression is no longer valid. I mean, the Boltzmann approximation is no longer valid to get that simple expression. Yes, you can still use the Fermi function. The Fermi function is still valid, but it's a more complicated integral. Was that your question? For that number of n c, that's for silicon at room temperature. Yes, this is for silicon. This value of n sub c is for silicon at room temperature. That's right. There was another question. So the expression is here, right? So this kT. So that's a good point. So let's say this is an example. Like if you have to do this on a quiz, we give you this value of n sub c at room temperature. And let's say I tell you that the effective mass really doesn't change much with temperature. But I ask you, if I double the temperature, how will n sub c change? You don't have to actually plug in all those numbers and recalculate. You can just take into account that it's the temperature to 3/2 dependence, right? So all you have to do is just multiply by the square root of 2 to the 3/2. I mean, by 2 to the 3/2 power, right? Well, I'll give you some numbers that's easier than that, right? Like 4 to the 3/2 power. You can calculate that, right? It's 8 times. All right. Good. So for holes, same thing, except you integrate over the entire valence band range of energies. So you integrate from E sub v all the way to -infinity. Again, we sort of approximate. Makes it easier to come up with a simple analytical expression. So you multiply the number of allowed energy states in the valence band and multiply by 1 minus the probability that they're occupied, right? So this is basically probability that a state is empty. So you see a similar expression for holes as for electrons, but now it's the separation between the Fermi level and the valence band energy the valence band edge energy that matters. Okay, so EF minus EV, again, N sub V is analogously, is the effective density of states at the valence band edge. Okay? And notice there's a difference in the expression for the effective density of states for the valence band versus conduction band is just due to the difference in effective mass for holes versus electrons. So it's just slightly different. Okay. So here then, so qualitatively, as the Fermi level becomes lower than the valence band, as the Fermi level goes above the valence band energy, you have this term in the exponent grows in magnitude, so the concentration of holes goes down exponentially. Let's see. I think I have. So let me show you the applet here. Oops. Okay, so if you go to the class website, there's those educational applets. So this is how we keep track of the number of electrons and holes on the energy band diagram. We just denote that by the Fermi level. So the Fermi level is closer to the conduction band. The probability of occupancy of states in the conduction band goes up. Okay, so you can see that that lobe over here grows. So the concentration of electrons goes up. If the Fermi so this is an N-type material, if the Fermi level is closer to the conduction band edge. If the Fermi level is drawn closer to the valence band edge, then the probability of occupancy, so the probability that states in the valence band are empty goes up, and you have more holes. Okay, so this is how we keep track of electron and hole concentration. We just keep track of it by drawing the Fermi level at the appropriate position within the band gap. Okay? So remember, the Boltzmann approximation is only valid if the Fermi level is at least 3 kT away from the conduction band edge or the valence band edge. So basically, that means that the Fermi level shouldn't be closer than, let's say, a tenth of an electron volt from the conduction band edge. Okay? So we'll come back to this at the end of the lecture today. But just qualitatively, do you see how we keep track? Right? The total integral of this distribution up here, that's n. The total integral of this distribution in the valence band edge is p. Okay? And you basically keep track of n versus p by the position of the Fermi level. Okay? Okay, so let's look at the case of an undoped semiconductor. So we can come up with a nice expression. At the end of the very first lecture and during the discussion section this week, we sort of showed you Ni, the intrinsic carrier concentration, as a function of temperature. So we can actually derive this expression now for intrinsic carrier concentration. And we do that simply by taking those equations for N and P and multiplying them together. Okay? So then you end up, and we know that in thermal equilibrium, the NP product should equal to Ni squared. So this gives us an expression for the intrinsic carrier concentration in silicon or some other semiconductor material. All you have to do is use the correct energy band gap value and the correct density of states for N sub V and N sub C. So what I show here on this slide are just values of N sub C and N sub V for silicon, germanium, and gallium arsenide. Some of the numbers are in red because there might be a discrepancy with one or more textbooks, but these are the values that you should use for our class this semester. Okay? And these values are consistent with the values of effective mass that I've given you in the previous lecture. So notice that the intrinsic carrier concentration depends exponentially on temperature. As you increase temperature, this exponential term gets smaller. So it basically gets bigger, right? Because e to the minus something over kT. So as you go to higher temperature, that exponential term grows very quickly. Also, NC times NV, the square root of that, it has a temperature to 3/2 power dependence. So that's why the intrinsic carrier concentration has a very strong temperature dependence. Okay? And hopefully you remember that Ni in silicon is roughly equal to 10 to the 10 per centimeter cubed at room temperature. Okay. So the question is maybe, well, so sometimes it's actually easier to keep track of electron concentrations relative to the intrinsic carrier concentration because it's a nice round number. 10 to the 10 is a lot easier to remember than n sub v and n sub c. So who can remember n sub c and n sub v right now without looking at their notes? Oh my god. Okay, but it's a lot easier to remember that n sub I is 10 to the 10, right? Right, okay. So therefore, it's actually nicer to be able to remember expressions for n and p in terms of n sub I. So it just turns out then, if you can derive, let's just derive this equation, for example, for electrons, okay? So what you need to know is E sub I. Okay, so E sub I is defined to be the Fermi level location for an intrinsic semiconductor. In other words, you have equal numbers of electrons and holes. Okay, you haven't doped it to make one, a majority carrier and the other one minority. So E sub I is defined to be the location of the Fermi level when you have equal number of electrons and holes. So the expression for n we got from the previous slide. And in an intrinsic material, that's going to be, n is going to be equal to ni. And so the energy, the Fermi energy is defined to be E sub I in that case, right? So E sub I is defined to be E sub f for an intrinsic semiconductor. Okay. So you can rewrite n sub c as a function of n sub I and E sub I, and then plug that back in. So let's do this. N equals n sub c. Is equal to ni e to the ec minus ei over kt. Right. So okay. So that's n sub c. Right. So that basically, I'm just writing the expression here, times e to the minus e sub c minus e sub I over kt. And did I write something wrong here? This is e sub c. Wait, hold on. The previous slide. And e sub c minus e sub f, sorry. E sub c minus e sub f. Right, okay. So then that's how you end up with that first expression. Okay? And the same thing you can do for the holes to derive this expression for p as a function of ni. All right, so I think a lot of times it's just easier to remember these expressions. But now it's the Fermi level difference between, between the Fermi level and the intrinsic Fermi level that you have to keep track of, rather than the position of the Fermi level relative to the conduction band edge or the valence band edge. Okay? So let's find out, where is that intrinsic Fermi level, E sub I? Well, to find that, we can take advantage of the fact that in an intrinsic material, n equals p, so we can set to be equal those two expressions for n and p, that's shown here. Then we can actually derive then that E sub I is very roughly equal to E sub c plus E sub v over 2. In other words, it is located roughly in the middle of the energy band gap. So for the exams for the exams in this class, it's sufficient for you to just draw an energy band diagram with E sub I drawn at exactly halfway between the conduction band edge and the valence band edge. Okay? Okay, so let's go back to, let's see. Right, okay. So let me just summarize. Let me turn on the lights. Okay, so let's draw the energy band diagram. E sub c, E sub v. Oops. Okay, so qualitatively, if I draw the Fermi level closer to the conduction band edge, what am I doing to the electron concentration? Increasing it. Very good. And I'm increasing it exponentially, actually. But now let's just draw the intrinsic Fermi level, just for reference. The intrinsic Fermi level is located halfway roughly between the conduction band edge and the valence band edge. So as I move E sub f away from EI, okay, so this is EF minus EI, I'm actually also increasing the electron concentration. So we can look at it two ways. So the two equations for n are simply like this. If you move the Fermi level if the Fermi level is closer to the conduction band edge, then the electron concentration comes closer to the effective density of states of the conduction band. So another way to look at this is if you raise the Fermi level to be closer to the conduction band edge, you're moving it farther and farther away from the intrinsic Fermi level. In other words, you're making electron concentration greater and greater than the intrinsic concentration. So you can look at it whichever way is convenient. You can think of moving the Fermi level to increase the electron concentration relative to the intrinsic, or moving it closer to make it come closer to the effective density of states. Either way is fine. But in terms of doing the calculations, it's a lot easier to deal with 10 to the 10 instead of 2.82 times 10 to the 19. Okay? So that's, so I showed you in the applet online this illustration. So if the Fermi level is closer to the conduction band edge, you'll have more electrons occupying allowed energy states in the conduction band. So the total, integrated amount of electrons, this is basically n, goes up exponentially. Okay, so let's just do a very simple exercise. And from the homework that you just turned in, this should be relatively straightforward. So the question is, where is the Fermi level for n equals 10 to the 17? So let's draw the conduction band edge and the valence band edge. Let's start out like that. Let's assume this is silicon at room temperature. So this is 1.12 electron volts. And we can draw the intrinsic Fermi level halfway, like this. OK, so let's So which equation do you want to use, actually? Now let's use the easier one. So let's do n equals ni. So hopefully you can sort of remember this. So it's ni times an exponential term, and this exponential term should get larger as the Fermi level goes higher than E sub I. Right? So that's like EF minus EI over KT. Okay, so hopefully you can remember that. So this is equal to 10 to the 17. And Ni is 10 to the 10. Okay, so hopefully this looks kind of familiar to you from your homework. So let's solve this. So basically, 10 to the 7 is equal to e to the EF minus EI over KT. Oops. Okay, so let's say we take the natural log of both sides. So that's going to be EF minus EI over KT. And here we go. We have EF minus EI equals KT times the natural log of 10 to the 7. So what's the next step here if you don't have a calculator? 7 times, right? 7 times KT times the natural log of 10. So what is that? Oops, 60 millivolts. 60 electron volts. So it's 0.42 electron volts. Okay, so you should be able to do this on a quiz, except I probably won't give you 10 to the 17. But anyway, okay, so E sub F. Okay, so this is 0.42 electron volts. Now you know that some people still like to use the conduction band edge as a reference. So if you know that the conduction band minus the valence band energy is 1.12 eV, then you know that this is 0.56 eV. So if you really wanted to, you can calculate that value as well. It's 0.14, right? So this is the energy band diagram for an n-type. Well, it's n-type because the concentration of electrons is much higher than the concentration of holes. What is the concentration of holes in this example? 10 to the third. Okay, so there's only one Fermi level for any material in thermal equilibrium. So remember the equation for holes? So P is equal to Ni e to the something. What is that something? Right, so it's EF minus E. Oops. Okay, hold on. Okay, I got it. That's right. It's EI minus EF over KT. Now you remember, because if the Fermi level moves down below the intrinsic level, you're making it more p-type. So the farther you move it down below the intrinsic level, the more you're enhancing the hole concentration above the intrinsic hole concentration. So here, EF is actually, well, this EI is lower than EF. So this is sort of an exponentially, like, really small term. So the hole concentration is therefore exponentially small, much smaller than Ni. Does that make sense? Okay, so the same Fermi level can be used to determine the electron concentration and the hole concentration. That's the point. Now later in class, we'll learn that if you shine light on the semiconductor, NMP product will no longer be Ni squared, so you cannot draw a single Fermi level for that material. Okay? Yes, question? The question is, okay, how do you answer this question? When I'm asking where is EF, yeah, you basically, the answer would be that EF minus, you can say EF minus EI. Okay, so you can say EF minus EI is equal to 0.42 EV. So we know that it's higher than EI by this amount. Or you can say that EC minus EF equals 0.14 EV. Either way is fine. Okay? I guess you could say EF minus EV, but usually pick the smallest distance. Okay, any questions about how to draw the energy band diagram? Yes?
My question is, like, to determine where it is,
If it's in the conduction band? Near the conduction. Yes, you're absolutely right. Yes, so the correct answer qualitatively is yes, EF is nearer to the conduction band edge than to the valence band edge because it's n-type. But if we want a quantitative answer, then you do need to specify this distance of the EF above EI. Yes, I will ask for a numerical, it'll say numerical answer required. Okay, so just curious, so we just solved this problem for n is 10 to the 17. How would you easily get the answer for 10 to the 16? If you know the answer for 10 to the 17 is 0.42 EV above the intrinsic level, what would be the answer if this n were 10 to the 17, it's 10 to the 16 instead? Exactly, right? So very quick. So if I give you an energy band diagram with EF minus EI is 0.12 electron volts, what would N be? 10 to the 12, right? And what would be P be? 10 to the 8th, right? All right, good. So that's how we keep track with an energy band diagram, the concentrations of electrons and holes in the semiconductor. So now we can keep track of not only the potential energy, but also the concentration. Okay, so last time, yes, question? So we'll come back. I think that's in the next slides. So towards the end of this lecture, I'll mention that. Yes, what happens if you dope really heavily? Like I said, typical doping concentrations can go up to 10 to the 20, and that's a special case. So that's what we call degenerately doped. So I'll cover that in a few minutes. So last time I mentioned that we should just assume in this class that at room temperature, where IC devices are operated, we can just assume that every single dopant atom contributes an electron or a hole, depending if it's a donor or an acceptor. So let's check this assumption to see if it's reasonable. Okay, so that's the point of this example. So let's consider a sample that's doped with phosphorus and to a concentration of 10 to the 17 per centimeter cube. Okay, so we actually just already did that. And so we know, okay. In any case, so if we assume that every single one of the donors contributed an electron, then that means that we're assuming that n equals n sub d, okay? And we already solved this problem before. But anyway, this means that I guess I rounded it differently here. But the Fermi level is, let's say, 147 millielectron volts below the conduction band edge. Okay, so let's just draw that. So we know the Fermi level here. It's not perfectly accurate, but anyway, 147 eV. Okay, so but remember that phosphorus actually has some ionization energy that's not 0. So let's draw that. So phosphorus, it turns out, has that fifth electron energy level is represented by a level that's close to the conduction band edge. Okay, so let's call that the energy level of that donor. And that ionization energy, here is, what is it, 45 millielectron volts. Okay, so remember, so the Fermi level, the donor energy level is very close to the conduction band edge. So if the Fermi level truly were, 147 millielectron volts away from the conduction band edge, we should be able to calculate using the Fermi function the probability that this donor level is occupied. Okay, so if a donor level is occupied, that means that it didn't contribute an electron to the lattice. In other words, it is not ionized. So this is the Fermi function here. And for the energy that we're of interest, is E sub d. Okay, so we can calculate this probability of occupancy of a donor state, and it's only 2%. So roughly what this means is that n is equal to 9.8 times 10 to the 16 per centimeter cube. I mean, just roughly. Because what you have to do to really find the exact energy levels, now you have to plug this value of n back into the equation in the middle of the slide, right, to find the Fermi level and then recalculate the probability of occupancy. And you just iterate until you find it converges to some self-consistent solution. But in any case, the probability that the donor is not ionized is pretty low. So that's why in this class we'll just assume whatever dopants are added to the semiconductor, you can assume the majority carrier concentration is equal to that concentration. E sub d, oh, that's the donor level. So this is for the, E sub d is the energy level for the fifth valence electron for the donor. And it's easy for that fifth valence electron to easily escape and become a conduction electron. So that means that energy level is very close to the conduction band. And that energy level is the ionization energy that we gave in the last lecture. So the ionization energies are pretty low for phosphorus and arsenic and for boron in silicon. Okay? Yeah, so actually in some old quizzes, I have asked people just qualitatively, illustrate, and this was in the last lecture, so illustrate a donor energy, electron energy level. So you would have to just draw something like that. Or if I asked you to illustrate an energy level associated with an acceptor, you would just draw it like down there. Because an acceptor easily accepts a neighboring covalent bond, covalently bound electron. So it's easy for an electron to move from the valence band into this acceptor state and leaving behind a hole that can move around. Okay? Yes? Oh, so this is basically probability of non-ionization. So this is telling you that 2% of those donor atoms are not ionized. In other words, they didn't contribute. So you take away 2%. Did I? Yeah, I think that's correct. Yeah, okay. Right. Okay, any other questions? Okay, p-type we sort of went over online. So p-type material, the Fermi level is closer to the valence band edge, so you have more holes than electrons. Okay, so to answer John's question here, what happens if we dope it heavily so that the Fermi level comes closer to the conduction band edge or the valence band edge, closer than 3 kT? So yes, those simple expressions for N and P were derived assuming that the Fermi level is not that close to the band edges. Okay, so in other words, a Fermi level is somewhere here in order for those simple exponential formulas to be valid. But if we dope a semiconductor very heavily, then the situation changes. Okay, so in this case, we call this kind of a semiconductor non-degenerately doped. And let's see. So what does it mean in terms of dopant concentrations? It turns out that if you do the calculations, this means that the dopant concentration is really not greater than 10 to the 18, just a rough number. Right? Just keep in mind, if you dope a semiconductor at 10 to the 18 per centimeter cubed or higher, then you can't use those. It's not valid to use those simple equations for calculating electrons and holes concentrations. Okay? So just roughly, just keep in mind, order of magnitude 10 to the 18 per centimeter cubed. Okay, so N-type means that you have many more electrons than holes. P-type means you have many more holes than electrons. So in this class, we use the terminology N plus to indicate a degenerately doped N-type material. So that means it's doped more than 10 to the 18 per centimeter cubed with some donors. And similarly, we call a material P plus type, or we can draw a semiconductor device. If some regions are labeled P plus, that just means it's doped more heavily than 10 to the 18 per centimeter cubed. But in terms of drawing energy band diagrams, to keep it just simple in this class, just assume that the Fermi level is located at the conduction band edge, and for N plus material. And for P plus material, the Fermi level has to come closer to the valence band edge. Let's just assume that the Fermi level is located at the valence band edge for P plus material. Yes, Ali. What exactly is degenerate about this? I guess maybe, well, it's just terminology. That means that fundamentally the properties of the semiconductor are going to be altered because the band gap energy, and that's the separation, that's sort of EV minus EC minus EV, that's going to start to be affected. If you introduce a significant, like close to atomic concentration of impurities into the semiconductor, then you're going to affect that periodic potential significantly. And so the band gap energy actually starts to become affected by the presence of the dopants, because now there's a significant number of them around. And so that's shown on this slide. The reduction in energy band gap, in the band gap energy, will increase as you increase the dopant concentration. Okay, so for example, even already at 10 to the 18 per centimeter cubed, the band gap, energy band gap measured experimentally is already a few tens of millielectron volts smaller than 1.12 EV. And if you dope it even more heavily, the band gap gets decreased more by 75 millielectron volts. Yes, question? Pardon me? Is it possible to close the band gap? That's an interesting question. I don't think so. No, it'll always be a semiconductor, right? If you close the band gap energy, if you eliminate the band gap, then it becomes a metal. Even degenerately doped semiconductors are not truly metallic. Yeah. Okay. So here's a simple analytical or empirical formula if you want to calculate the concentration of, the band gap reduction as a function of temperature and the dopant concentration. You can use the simple analytical expression. Okay? So qualitatively, the way I remember this is that, remember if you look at the energy band diagram, I drew it on a previous slide, right, on the left here, donors introduce allowed energy levels a distance away from the conduction band edge, and acceptors do the same thing. So essentially, if you have too many of these around, then you effectively, will end up reducing the band gap a little bit. Right? So qualitatively, it makes sense. It becomes easier for an electron from the valence band to come up and hop over and eventually go to the conduction band if you have a lot of dopants around. Yes?
You said it has to do with like the periodic one, but what?
Okay. That's a good question. So the question is, what if you have both acceptors and donors? Yeah, so that's what we call a compensated semiconductor, when you have dopants of both types. That's a good question. It's probably this kind of a plot, but it's the sum, the sum of the donor density and the acceptor density. So it's not the difference, but it's the sum. So maybe like, yeah, you have to add those dopant concentrations together, and together they will decrease the band gap. Right. So you could add both types of dopants together and get a very small, a much smaller band gap. That's right. Good question. Okay, so finally, let's just summarize then. Looking at the expression, the less easy expression for electron concentration, bottom line is if you've moved the Fermi level closer to the conduction band edge, that means that's corresponding to the higher electron concentration. In other words, the higher dopant concentration, n-type dopant concentration. So that's what's shown here, right? This separation between the conduction band edge and the valence and the Fermi level decreases as you increase the doping exponentially. Okay, and same thing here. This separation between the Fermi level and the valence band edge gets smaller as you dope it more heavily p-type to make it more, with acceptors. Okay, so the final detail here is the effective temperature. So remember at the beginning of the lecture today, what did I say? If you go to very high temperature, if you raise the temperature significantly, what is the biggest impact of raising the temperature? More intrinsic carriers. And remember, where is the intrinsic Fermi level located? Near mid-cap. Right. So as you heat up a semiconductor, you have more intrinsic carriers. The carrier concentration, the total electron concentration and total hole concentration is going to get influenced more and more by the intrinsic carrier concentration. So the Fermi level actually, as you heat it up, gets closer and closer to the intrinsic level, because intrinsic carriers are starting to contribute more and more significantly. So you have, you're balancing. So intrinsic carriers are generated in equal amounts of holes and electrons. So if the number of holes and electrons is getting closer because Ni is getting higher, Fermi level will come closer to intrinsic level. So that's what's shown here. As you increase the temperature, the Fermi level comes closer to mid-gap, where the intrinsic Fermi level is. Okay? So the energy band diagram will depend on temperature as well as on the dopant concentration. Okay? Any questions about this material? So remember, this is all assuming thermal equilibrium, so there's no significant electric field, no light shining on this. If you want to be precise, you have to use the Fermi function to calculate the probability that this energy level is occupied in the conduction band or the valence band. And the probability of occupancy depends on the location of the Fermi energy. And you can use the Boltzmann approximation if the Fermi level is not too close to the conduction band edge or the valence band edge. And I'd say it's always, for me, for the quizzes, it's easier to remember the Ni version of these equations, right? So remember 10 to the 10. Okay, what's n sub v? See, okay, that's my point. You still remember it? Okay. 10 to the 10 is easier to remember, right? So I think for the exams and quizzes, it's adequate just to remember this form of the equation. Okay, so Fermi level higher than EI means it's n-type. Fermi level lower than EI is p-type. Or you can say Fermi level closer to the conduction band is n-type. Fermi level closer to the valence band is p-type. Whichever way you like to remember it is fine. Okay? And for degenerately doped, let's just keep it simple. Just draw the Fermi level. So if I were to draw a Fermi level like energy band diagram like this, what kind of material is this? N plus, right? N plus. Very good. All right, and then later, if we draw this, that's P plus. That's the band diagram for P plus. So yeah, fine detail is that yes, the band gap energy is smaller, but let's just keep it simple. We can just assume it's 1.12 eV, just the Fermi levels, either at the conduction band edge or the valence band edge for n-type, p-type degenerately doped material. Okay, and that's it. Thanks, and have a good weekend, and see you next week.